we're going to have a synchronous lesson, so you can do this when it suits you. Just have it done for Thursday, and I'll be checking your work. So the first thing I want you to think about is just a little recap. These terms here, MR, AR, mole, and mass, right? I want you to write down what you think. The first thing I want you to think about is what each of these means. And the second thing I want you to do is think about connections between them. So how are they related to each other, if at all? Okay, so pause the video at this point, have a think about those, and then play the video and see what you come up with. So I've just put a few notes here, and what I was thinking, just an idea. This is really just how to connect what you know before. So your AR is relative atomic mass, MR is relative formula mass. To get the relative formula mass, you add together all the relative atomic masses in the formula. Relative atomic mass is relative to the carbon-12 isotope. And then the relation, a mole is 6.022 by 10 to the 23 of anything. It's that number. The 1 mole of a substance, or sorry, the relative formula mass of a substance in grams contains 1 mole of it, right? And then the relationship between mole mass and MR, mole is equal to mass divided by MR. Now, the layout of this can be different for you, and you might have more detail, but really it's just to connect you into what we're doing today. So today what we're going to look at is 2 things. We're going to manipulate the moles is equal to mass over MR equation, and we're going to start looking at what's called reacting masses. Really, that's where we want to go to. So ultimately, what you will be able to do, right, is if you know, right, so say you have a chemical reaction and 2 random chemicals, A and B, form C. So if you know the mass of A, right, you can work out the mass of C formed, right, using the idea of the mole. So we're going to look ultimately at how, if you're given the mass of one substance, you can work out the mass of the other substance that it reacts with or what it forms, but you need to know the moles to do that. So we're going to be sort of starting looking at that, because actually ratios, and by that I mean the idea that maybe you have 2A and 3B gives you 5C, just depending on how the ratios, right? So we're going to call those mole ratios, I think that's the term we're going to use. So we're going to sort of work at that first. So we're at the bottom of page 8. So if you remember the last Tuesday, we were doing some calculations on moles. So if you go to, I'll have the one note in here. So if you check the one note, you will see there is the blank notes, right? And you were doing these questions the last day, and some of you got further than others. I think some of you got it finished. So if you didn't get a chance to check, or you want to have a practice of that first, using the idea of moles is equal to mass over MR, you can have a go, and all the answers are in the quantitative chemistry with answers. But we are going to move on to the next part of this. Let's see if I can click into it, which is just manipulating this idea, this ratio. So some questions, we're not there yet. Okay, so we're going to be starting at the top of page 9. But before that, I want you to have a look at the screen and just remember that moles is equal to mass in grams divided by relative formula mass, or relative atomic mass if it's an element, but that's less common. So we tend to just write it as relative formula mass. Okay, so what I want you to do is, again, pause the video, and I want you to rearrange the equation to get mass. Okay, what if you rearrange it? If you want mass on the left, what do you have on the right-hand side? And lastly, rearrange the equation to get MR. So I want you to pause the video at this stage and rearrange the equation to get those 2 expressions. Okay, so you should have got mass is equal to moles times MR, and MR is equal to mass divided by moles. Now, either you can learn those, right, because you do need to use all 3 of them. Oops, great square there. Or you can just rearrange them as you go. Now, I know some of you might like using formula triangles. I'm resisting a formula triangle. Okay, I am going to resist it. But I'd rather that you were able to manipulate these expressions to get to change if you have the unknown for different unknowns. So with that in mind, what I want you to do is in the notes on page 9, I want you to try the equation question 29 and 30. Okay, so question 29 is the idea of mass is equal to moles times mR, and then question 30, you're required to look for the mR. So pause the video, have a go at those questions, and I will put the answers up. You can check when you're finished. Just to say, if you do need some extra help with that, just you can go to the OneNote and they are worked out. Okay, so I'm going to switch over to the OneNote now and show you, talk through the first couple. So you can see they're 29A. They've actually given you the answer, so you can check that you've rearranged the equation. So 5 moles of Cl2. Now, I should have mentioned that again, you're going to have to work out your MORs, right? So this is quite common, that you will be given either mass or moles, and you will have to work out the MOR. So don't forget that you have to do that. So for Cl2, it's 71, right? Where are we? Okay, so 71, so 2 times 35.5. Okay, so which is equal to 71. So you can prove that 5 times the MOR, which is 71, is equal to 355 grams. Okay, so again, aluminium oxides, MOR is 102, right? So 0.2 times 102 is equal to 20.4. For C, it's AOR this time, relative atomic mass, which is 108 for silver. I think I've called it AG. No, AG's are relative atomic mass, and that's 0.01 times 108 is 1.08, and so on for D. So just double check that you got your relative formula masses correct. Because if you made a mistake, that's the most likely place a mistake was made. Now, for question 30, you had, this time you wanted MOR and you were given mass and moles. So just have a look at the question, and you see here that they've given us a little more detail here. So in this instance, you've been given the mass of 1 gram. You've been given the moles of 0.00568. So to find the MOR, you divide 1, which is the mass, by 0.00568. And that's how you get the answer of 176. So just to remind you, this is the definition of the mole, okay? Although, as I say, at this stage, you do not have definitions. Yes, the mole is, as a number, is 6.022 by 10 to the 23. But actually, this is the definition that the exam board wants, that 1 mole of a substance is its relative formula mass in grams. Now, the reason they do that is because actually the whole Avogadro's number isn't on GCSE, but I always I introduce it because I think it's hard to really conceptualize or think about the mole if you don't think of it as a number and you don't know exactly what that number is. Now, we're going to move on to the idea of manipulating ratios. So I had mentioned earlier on that you're going to ultimately find, if you're given the mass of one substance in a chemical reaction and you know the balanced chemical equation, you can work out, and you know all the formulas, the reactants and products, you can work out the mass of any other substance in that reaction, right, just by giving one mass. But in order to do that, you need to understand how to manipulate ratios, including mole ratios. But we're just going to look very briefly at a sort of more called a concrete example, something that you might understand a bit more before we look at actual chemical equations. So let's have a look at how this works in a sort of everyday context. On a youth camp, there must be a ratio of at least 1 leader to 6 children. So say that's an idea. I mean, you'd understand that if you've gone away anywhere, you've gone on school trips or whatever, especially at primary school. There's always a requirement to have a certain number of teachers per child, or, you know, if you're in scouts or whatever, you'll know that there's a requirement to have a certain number of adults for every certain number of children. So say it's 1 to 6. Okay, so every time there's 6 children present, there must be at least be 1 leader, 1 adult present for that. So if there are 12 children, okay, obviously you need 2 leaders, 2 times 6. Okay, so in this instance, obviously you've multiplied the 6 by 2, so you must multiply the number of leaders by 2 as well. Okay, if you have, so that's fairly straightforward. Okay, so you've represented it here. You've doubled the number of children by 2, so you double the number of leaders by 2, and you still got the same ratio. However, what happens when you have sort of a less obvious number? So supposing you need a 1 to 6 ratio, right, of leaders to children, but you have 100 children present. So you're going on a school trip, you need 1 adult for every 6 children, you have 100 children in total, say 3 classes going, right? How many leaders do you need? So how do you go about deciding that? So what it says here is the easiest thing to do is do it in 2 steps, right? But you have to do the same to both sides of the ratio. So if we want to find out how many leaders you need per child, you divide by by the ratio. So you're going to have 1 over 6. So that will give you 1, and then 1 over 6. So I think here it's done it as a decimal, but let's put it as 1 over 6. So you need 1/6 of a leader or adult for every 1 child, right? That's how the ratio works out that way, okay? Okay, but you have 100 children, so you just multiply each side now by 100. Okay, so now you've 100 here and you've 100 over 6, which is equal to, must be 100 over 6, so it rounds up to 17 to 100. So for every 100 children, you need 17 leaders. Now, obviously, it's probably a smaller number than that. It's probably a decimal, but you can't have like parts of a person. So it has to be rounded off to a whole number. Okay, so you would do that again. Okay, so how does that work? Let's have a look. So the simple method can be applied to any ratio. So let's have a look and see if we can do another one. So using that idea, can you work out how many leaders are required for those numbers of children, including a mole of children? And again, the answers are all worked out on this second sheet in the OneNote. So what I suggest is you have a go and maybe have a look at 1 or 2 yourself and see how you get on. And you can see here that when I've done it, say for the first one, it works out at 6.68 litres for 40 children, but you'd round that up to 7 because you can't have a part of a human. So work that through, see if you can manage that and manipulating the ratios. And when you can do that, it should be easier to do when we look at chemical equations as well. So we've got, so whatever you do, okay, so leaders to children, 1 to 6, divide each side by 6. I've done it as a fraction here, and then multiply by the number of children that you have. Multiply and you will get your answer. Okay, so can you try that? And then when you're ready, I'll pause the video, have a go with that, and then check your answers. Now for question 32, it's actually easier because you just need to multiply the number of leaders by 6 because it's a 1 to 6 ratio. So each leader can supervise 6 children. So you just multiply to get the number of children they each can supervise. And again, check the answers in the next sheet. Now for question 33, right, I'm just going to show you how to do this and then you can carry on with it. Okay, so this time it's 3 to 11, right, so slightly more difficult. Okay, so really what we're doing is, again, we're just dividing, we want it as a ratio, something to 1. So we're going to divide by 11 of the children, right, and we also divide that by 11, right, so it's 3 over 11 to 1. And then what you multiply, so each question will ask for a certain number of children. So say for A, it's by 22. So you would multiply by the number of children here. Okay, obviously, I'll give you the actual number. And then same over here. So you do the same to both sides. And you will get your answer. And again, if it's for 34, how many children can be supervised by a certain number of leaders? This time, you want to divide by 3. So you want to find out how many children for every 1 leader, right? So you divide by 3 this time. So every 1 leader can supervise 11 over 3 children. Okay, so 36 leaders will give you 36 by 11 over 3. So that, I'm going to cheat and check the next page. So that would be 133.2, or approximately 133, 134 children. Okay, so have a go with those questions. Check the answers when you're ready, and pause until it's done.